Hello students, next we look into the conjugation property. In the conjugation property, if we already know what is the z transform of x of n, which is x of z, which has an ROC, a region of convergence, which is given by some region R, then what the conjugation property says is that if you want to take the conjugate, if you want to take the z transform of the conjugate of the function x of n, all you have to do is take this particular function of z, and instead of z substitute z conjugate, and instead of the whole function substitute its conjugate. Now you might be thinking that why we are saying, or what do we mean by saying the conjugate of z? See, z is generally given by r e raised to power j omega, and conjugate of that means minus of j omega. Okay, let us prove this. We already know that the z transform of x of n is given by this particular formula, x of n summation n from minus infinity to infinity, x of n z raised to power minus n. Then to take the z transform of x conjugate of n, instead of x of n I will substitute x conjugate of n. That's all. Now for solving this, what we will do is we will write z as a conjugate of conjugate. Now we already know that if there is a function z, that can be written as the conjugate of the z conjugate. Why? Because z is equal to e raised to r e raised to power j omega. If I write conjugate, then it is minus j omega, and if I take the conjugate of that, then it is again minus of minus j omega, which is actually plus of j omega. So it comes back to z. So z can be written as z conjugate conjugate. Now since there are conjugate in both these, I will take commonly conjugate outside, and I will write it as, I will put the whole bracket and take the conjugate outside. So now what is this function? See, this function is basically the z transform of x of n, with the only difference that z is z conjugate. So it means that it is the z transform of x of n, with the difference that instead of z I will have to write z conjugate, and that is what we have written here, and then the whole conjugate is there outside. Therefore I can say that the z transform of n, x conjugate of n, is basically x, capital X conjugate of z conjugate. Next property is the convolution property, which says about the convolution sum between two functions x1 of n and x2 of n. So suppose if you are having x1 of n, whose z transform you already know is x1 of z, which has an ROC region R1, and another function x2 of n, which has a z transform x2 of z, which has an ROC which is region 2 R2, and we know that when we do conjugate in this particular time domain side, then the convolution between x1 and x2 in time domain will lead to multiplication between the two z functions in the frequency domain. And this is a very important property, because whenever we are talking of convolution, then instead of doing convolution, we can do multiplication of their z transforms. So what happens to the ROC? ROC is going to be the intersection of the two regions. R1 and R2 are two regions of x1 of z and x2 of z. Then when we multiply both of them, the ROC will basically be the intersection between the two regions. Now let us look at the proof. So when we want to take the z transform of any function, we write that function multiplied by z raised to power minus n, with summation n going from minus infinity to infinity. Now I am going to substitute the equation of convolution that we have already studied. So I have used a different color. So we know that we have to use the convolution equation, and convolution between two sequences x1 of n and x2 of n we have already seen. It is basically given by this equation, which is summation k is equal to minus infinity to infinity x1 of k, this is small x1 of k, into small x2 of n minus k. This is a very well known convolution equation. Okay, now in the next step what we do is we are adding new functions z of k into z of minus k, because we know z of k into z of minus k is easily written as z of k minus k, which is 0. And what is z of 0? Z of 0 is equal to 1. So previously where we had here, we can simply write it as multiplication of 1, multiplication with 1. There now we have written zk into z raised to power minus k, and this we have added up a new here. That's why I have used a different color to show it. So we are introducing two terms here, and out of which I take this particular z of k and take it inside this function. So now I am having z of minus n minus k. So now interchanging the order of summation, so what I do is I take the k portion. So only functions which are having k, which are those functions? One is x1 of k and another is z of minus k. So these I take outside, so that I am having here, and this n and n minus k functions are written together, which I have written here. Now suppose if I am going to now substitute, instead of n minus k, if I am going to substitute p, where? Here. Then instead of x2 of n minus k, I can write x2 of p, and instead of z raised to power minus of n minus k, I can write z raised to power minus p. What about this summation? See, if I write here, when n is equal to minus infinity, then p is minus infinity minus k, which is minus infinity, and when n is infinity, then infinity minus k is as good as writing infinity. So here n basically changes to p, and with the same limit of minus infinity to infinity. So now this can be written as the z transform of x1 of k. So small x1 of k has got changed to x1 of z, because we have taken the z transform of x1 of k, and similarly this can be written as the z transform of x2 of p, which is x2 of z. Hence we have proved it. So we can say that x1 of n convolution with x2 of n in the time domain, will lead to x1 of z multiplied with x2 of z in the z domain, and the ROC is intersection of R1 region and R2 region. Why? Because of the multiplication. Next is the multiplication property, or the complex convolution property, wherein we have multiplication taking place in the time domain, which leads to a convolution in the z domain. Now the convolution of two z domain functions is basically given by this equation, because z is repeated from 1 by 2 pi j, and the integration is circular integral. But what I want you to remember here is that generally we don't use this formula, but this particular property should be remembered by all, that once you multiply in time domain, you have the convolution in the z domain. Generally we need not find out the z domain convolution. So to prove it, the z transform of x1 of n into x2 of n is simply substituting x1 of n into x2 of n with z raised to power minus n and writing the summation. Now, if we look at the inverse z transform equation of a function x of n, it is given by this particular equation. Again, the inverse z transform we do not have to find out using this equation. We have other methods to find out the inverse z transform, but we will use the equation for this particular derivation. So see here, this is the equation of the inverse z transform. Now in this particular equation, z is a complex variable r e raised to power minus j, r e raised to power j omega. Instead of z, if suppose we are going to consider it to be written as v, okay, and we use this inverse z transform equation for substituting instead of x1 of n. So here instead of x of n, if I am going to write for x1 of n, then basically I will get the equation like this, wherein using a different color I have shown where I have done the substitution. So instead of x1 of n, I have substituted the inverse z transform equation. Now instead of now if I change the order of integration and summation, that means I take this integration outside and the summation inside. So integration is with respect to v, so I take the v components outside and I take the n components inside. So you can see that this particular integration, the summation, has basically come inside, and since it is with respect to n, I have taken x2 of n z raised to power n also inside, and I have taken the integral x1 of v outside, okay, and I am going to put the bracket. I am going to write v raised to power n minus 1 because the n factor is there. So I will take v raised to power n inside this particular summation, whereas v raised to power minus 1, whereas I will take the v raised to power minus 1 and I will write it outside with dv. Okay. Now what I can see here is I can combine both of them together. So I will write this as v raised to power n into z raised to power minus n can be written as 1 by z raised to power n, which can be written as v by z the whole raised to power n, or I can write it as z by v the whole raised to power minus n. So that is what we have done here, z raised to power z by v raised to power minus n. So here whatever is inside the bracket, what is this? This is the z transform x2 of n, with the difference that instead of z, now we are having z by v. That's the only difference. So this whole function inside the bracket is the z transform of x2 of n, which is x2 of z, but instead of z we are having z by v, and that is what I have substituted here. And this you can see is the same equation that we are having basically here. Thus I can write that we have proved that convolution in time domain leads to multiplication in frequency domain. Sorry to have written like that. I will once again write this. This is multiplication in not frequency domain, z domain. Okay. So with this we have proved that property. Next is the accumulation property, which is similar to the integration property in Laplace. Okay, so what we are having is a signal x of n, and x of n has many different values for different values of n. If I add up all the values of x of n right from minus infinity to the present value n, then what I am having is an accumulation of xn. Okay, that is called as an accumulation of xn. That means you are accumulating one by one, you are adding up all the values that are there in xn at all values of n. Okay, so if you accumulate that, then what is the z transform of that function? The z transform of that function according to this is given by, if you know the previous z transform of x of n, then all you have to do is you have to multiply 1 divided by 1 minus z inverse with x of z. Let us prove this. The z transform of any function is given by multiplying that function with z raised to power minus n for a summation n is equal to minus infinity to infinity. So we have substituted that function. Now if we substitute n minus k as r, or if I write k is equal to n minus r, okay, that means I am going to substitute n minus k is equal to r, or k is equal to n minus r. So where is k? K is here, k is here, and k is here. So now we have to be careful because I am going to change this summation as well as this summation and this n. So this n is changed as k plus r according to this particular equation. N can be k plus r. So that n I am going to change to k plus r. So that let it be there. Now what I am changing these summations into? See, if I am talking about this n, then I am going to change that n to k. How do I change that? See, when n is equal to infinity, I will use this particular equation. So when n is equal to minus infinity, then the value of k will be minus infinity minus r. Whereas when n will be equal to infinity, then I will write plus infinity minus r, plus infinity minus r. That is what we have substituted here, which we know in the next step will become k is from minus infinity to infinity. Okay. Whereas for this particular summation, I will change k to r using this equation. Okay. How? By substituting k is equal to minus infinity. So this becomes n minus of minus infinity, which is n plus infinity. Okay. And the upper limit, that is n here, that I again substitute in place of k. So I will get n minus n is equal to r, which I will substitute it here. So n minus n is going to be equal to 0 and n plus infinity is going to be infinity itself. So, and since we have actually substituted n with k plus r here in this particular equation, in the next step I will split them up as z raised to power minus k and z raised to power minus r. Now here I am going to change the order of integration. How? I am going to take all the r components outside and I am going to take the k components inside. So if I interchange the order of summation, this will come inside whereas this will go outside, and that is what we see here. And with that, r z raised to power minus r will also go, and that is what we see here, that we have got r is equal to 0 to infinity z raised to power minus r, and then this one we are having. Now what is this? This is the z transform of x of n, which is now written as x of k. The variable has changed from n to k. So this is x of z, capital X of z. Whereas this particular equation can be reduced to another equation, because we already know that if we sum alpha raised to power n for 0 to infinity, we know that the answer is 1 by 1 minus alpha, provided that the alpha value has to be less than 1. So with that thing in mind, if I convert this particular summation, then I will get 1 divided by z raised to power minus 1 into x of z for this one, which I can write also as, substituting z inverse as 1 by z, I will get z divided by z minus 1 into x of z. Hence we can say that the z transform of accumulation of x of n, the accumulation of x of n, here I should have written n raised to power n, sorry, summation from minus infinity to n, x of k is going to be this function. Next we look at the another important property or theorem or relation, which is called as the Parseval's theorem or relation. Basically what Parseval's relation says is that if you calculate the energy at one domain, let's say the time domain, then the energy, and if you calculate the energy at the z domain, the energy will be same. Because see, when we are transforming a signal from one domain to another, we are only changing the domain of the signal. We never change the energy associated with the signal. So if you would calculate the energy at the time domain side and you calculate the energy at the z domain side, both the energies will be equal. So the energy at time domain will be equal to energy at the z domain, and that is what we are going to prove here, which is actually given by the equation. We know that the energy of any signal, so instead of having one signal we are writing two signals here, so that relation is very clear. So if I am having x1 of n whose z transform I already know, x2 of n also I know the z transform is x2 of z, then the summation n is equal to minus infinity to infinity x1 of n x2 of conjugate x2 conjugate of n. So you might be asking, sir, how is this the energy? See, when we say the energy, suppose if there is only one signal x1 of n, then we know that the energy is basically given by summation x of n, not summation, the absolute value of x of n square, summation from n is equal to minus infinity to infinity is the energy of this particular x of n. But absolute value of x of n can be written as x of n multiplied with x conjugate of n, correct? So that is what we have actually written here. We have just written two functions because mathematically also this is correct. Then in the z domain I have to do the integration of the two z transform function by taking the conjugate of the other side, the other function x2 of z, of the conjugate of z inverse. Okay, so let us prove this particular equation where we are already considering that x1 and x2 both of them are complex. Now you might be asking, sir, do we need to actually do this? See, all the properties that we have studied, whether it be Laplace properties or Fourier transform properties, everywhere we have studied Parseval's theorem. The same thing is actually being shown here, just to show that all the properties are there present in Z transform also, as it was present in Laplace transform as well as the Z transform. It does not mean that all of this will be coming in for solving some problem. There is nothing like that. But we can basically use these formulas at certain stages. That's why it is written. Don't worry, you will not be asked to calculate this right hand side equation in any of the examinations, because that is complex. Our major aim is to make the subject easy to calculate. Even if you pass out and use this somewhere, we should try to always use this equation. So it is just that equating, that if you want to calculate the energy, you can calculate it using the time domain side or the Z transform side. Obviously we will try to use always the time domain side because that is more easy. Okay, so now let us solve it, or let us prove it. So starting from the left hand side, we know the left hand side equation as such I have written. Now instead of x1 of n, if I substitute the inverse Z transform equation of x1 of n, so instead of this particular x1 of n, instead of this particular x1 of n, if I am going to substitute the inverse Z transform equation, now already I have previously told what is the inverse Z transform equation, so I will not tell that here. So if I do that, then what do I get? So I get this particular equation, which is the inverse Z transform equation of x1 of n. So I have written it in a different color for you to demarcate or differentiate between the two. So now I am going to interchange the order of summation and integration. I take this much portion of integration, I take it outside, and this summation with respect to n I take inside. Now this particular integration is with respect to z, whereas all the functions related to n, which is this one as well as this one, I will take inside the summation, and that is what we have done here. Okay, I have taken the z raised to power n function. Now you might be thinking that here I have written something. What has happened? See, z raised to power n minus 1 can be written as z raised to power n into z raised to power minus 1. That z raised to power minus 1 I have taken from here, I have taken it outside because it belongs to z. There is no n in it. So I have taken that outside, whereas the z raised to power n term, I have written it as z raised to power minus 1 the whole raised to power minus n, because we know that this is as good as writing z raised to power n. Why? Because minus 1 into minus n is going to be n. So that is what we have done here. Now my next aim is to take this conjugate outside. To take this conjugate outside, I have to write z itself as z conjugate of conjugate. So that when I take this conjugate outside, the other conjugate remains inside, and that is what has happened in this particular step. So I have taken the conjugate of x2 of n outside with the conjugate in this one. Also I have taken outside, and that both of those conjugate have commonly come here. So what remains inside is only x2 of n and the remaining z conjugate. Clear? Now whatever is inside this bracket is basically the z transform of x2n, with the difference that instead of z what we are having is z conjugate the whole raised to power minus 1. So instead of z it is this. So what we are going to do is, instead of this I am going to substitute and write it as x2 of z. Now instead of z I will write this, which is z conjugate the whole inverse, and this total conjugate that is outside in the bracket I will write it as x2 conjugate, and that is what we have done when we wrote this. Okay, with that we have proved, because this was what was the RHS side, the right hand side of the major equation, and thus we have proved it. Next is the initial value theorem and the final value theorem, starting first with initial value theorem. See, if there is a function x of n whose z transform we already know is x of z, with the condition that x of n is causal, meaning that x of n is only existing for t being positive values. That means t positive values only x of n is existing. There only we can do this initial value theorem. Okay, so with these conditions, if we know a function, then if we want to find out the value of x of 0, that means the first value of x of n, which is what is the value of x of n at n is equal to 0, that means x of 0, then all we need to do is find out x of z, and instead of z substitute infinity. Okay, that means take the function x of z and instead of z substitute infinity, you will get the value of x of small x of 0. Okay, let us prove that. See, we already know that for a causal signal, the equation of z transform will be given by this, wherein you can note that it is from 0 to infinity, because it's a causal signal, that is only for n is equal to positive values of positive values. So for positive values of n, that is from 0 to infinity, if I take the z transform, this is the equation. Now I am going to expand this equation, that means right from 0 to infinity. So n is equal to 0, it is x of 0 raised to power into z raised to power 0, which is 1. For n is equal to 1, it is x1 z raised to power minus 1. Similarly for 2, 3, all the way up to infinity. Okay, now z inverse can be written as 1 by z. Z raised to power minus 2 can be written as 1 by z square. So that is what we have done here. Now if in both this equation, if I substitute z, or if I put z tending towards infinity on both sides, the limit, or taking the limit, then you can see that if I put z is equal to infinity here, this portion will become 0. Similarly, if I put infinity square here, this will become 0. All these functions will become 0. On the right hand side only this will remain. Correct? So that is what we have done here. So when we substitute that, what we find out that all the other functions become 0, only x of 0 remains. Thus we can say that only x of 0 is remaining, small x of 0. So x of 0 if you want to find, all you need to take is take the function x of z, and at z apply limit infinity, z tending towards infinity. Next is the final value theorem, which basically tries to find the value or the final value of x of n, which is at x of infinity. So at x of infinity, if I want to find out, what it says is that all you have to do is multiply x of z with z raised to power minus, z minus 1. You multiply x of z with z minus 1 and apply the limit z tending towards 1. So you might be feeling that, if I put z is equal to 1 here, so 1 minus 1 will become 0. So the answer should always come as 0. No, when we say you have to put z minus 1 here, we are meaning that there will be some function in which this z minus 1 may get cancelled off. Okay, and that is why we have written here that, we are trying to find the final value of a function x of n whose x of z we know, and if x of z has no pole outside the unit circle, that is important. In only those cases we can find out the final value theorem. And it has no double or higher order poles on the unit circle centered at the origin. So it has no poles on the unit circle. So unit circle means if you are trying to draw, then it will have at this value 1, at this value is equal to minus 1. So it is not having any of those cases. Then in those cases alone we will be able to apply the final value theorem, which is basically this. Now let us prove this. Now we already know that for a causal signal, the function is going to be basically given by this. Now you might be asking all of a sudden how causal signal has come here. That is because of these conditions. Okay, because of these conditions. Okay, that makes it automatically x of n to be a causal signal. So we know that for a causal signal the Z transform equation is basically from 0 to infinity. Okay, from 0 to infinity. Now we have also seen the time shifting property, in which we have written the time shifting property with respect to x of n plus 1 if we are going to do, where the shifting is with respect to 1. Then this is the equation. Now where this initial condition x of 0 is already written here. Now when you look at the time shifting property, you will remember that there were two equations that I taught, where I added something in green color for the initial condition, and that initial condition is this one. Okay, so that equation you can once again check. Now this equation I am going to write as equation number 2, and this equation is equation number 1. Now here you will see that, this is the equation according to the property. Whereas what is the original equation of z transform of this function? All I have to do is, instead of x of n, I will substitute x of n plus 1 z raised to power minus n. Okay, now if I am going to subtract this equation with, if I subtract this equation from this equation, that means 2 minus 1, if I am going to subtract 2 minus 1, then you can see that this right hand side of this equation and this equation, so these two I am going to subtract. So I am going to do this minus x of z, and that is what is written here. Okay, and in the other part I am basically going to take this equation and I am going to subtract it with this equation. Okay, I am going to subtract it from this equation, so I will take this minus this. Okay, and that is what we have written basically here. Now from here, if I look, this is also summation n is equal to 0 to infinity. This is also from n is equal to infinity, 0 to infinity. These functions are common, only these two are there. So I can write a single summation, and I can write x n plus 1 minus x of n. I have written that together. Okay, and now in the left hand side we are having x of z and then minus x of z. So these two I can combine together and I will get z minus 1 x of z. Okay, now if I take limit z tending towards 1 in both sides, that means in this side as well as in this side. So in this side, all I'm going to do is I'm going to write the equation limit z tending towards 1. Here what happens when I put z is equal to 1, what happens? That basically z becomes 1, so I am left with x of 0. Correct? Here I have not substituted anything. Whereas in the right hand side, I am going to substitute this particular equation. In this particular equation, I am going to put, in this whole equation, I am going to put z is equal to 1. Then here 1 raised to power minus n is 1 itself. So in this equation, I am having into 1, which I have not written. Okay, so what remains in the right hand side is only this equation. Now if I expand this equation, see, if I put n is equal to 0, then here it will become x of 0 plus 1, which is x of 1 minus x of 0. For n is equal to 1, it will become x of 2 minus x of 1. Similarly, all the way it will go up to infinity and infinity minus 1. So you can see I can cancel this x of 1 with this x of 1. Okay, similarly I can cancel this with x of 2, this one. Similarly it will go all the way, I will able to be cancelled this one also. So what remains? What remains is basically this x of minus x of 0 and this x of infinity. Rest all will basically cancel off. And that's why this right hand side equation gets reduced to this value, whereas the left side I have kept it like this. Now if I write it all together, I will get in the left hand side this equation and in the right hand side this equation, where these two will cancel out, and I will basically get this equation which says that if you want to find x of infinity, all you have to do is multiply with x of z, a function z minus 1, and apply the limit z tending towards 1. Okay, with this we have completed all the properties of z transform, all the way from linearity property to the 13th property, which is the final value theorem. See, you all might be thinking, why should we study this property? See, the proof is something that is asked in the exam, that is true. That is the reason why we study. But we use this property to solve the problems, and that is what we will see in the next video. Thank you.